So now let's think about what happens when I don't have a static condition. In forces, if we weren't static, if we had a net force, then we said that the sum of my force net equaled ma. So let's recall that I said that inertia is the equivalent to mass, and alpha then is the equivalent to acceleration, to a. So this torque is actually a net torque. Does I have a net torque? Therefore, I'm going to have to move this mass in some way, and it will experience an acceleration. So this question that you're given is example 3 in the handout, page 13. It's the merry-go-round accelerates from rest, so omega naught equals 0, in 24 seconds. And it reaches 3 radians per second as far as its rotations go. So this is omega final. And assuming that it's a uniform disk. So let's see, we're assuming that it's a uniform disk. Assume the merry-go-round is a uniform disk. So this is when you open up your book to the page that do I have it open? I might have it open. Yes, I do. That is page 210. Page 210. If you open it up to page 210, then you will see for a uniform disk that I is 1/2 mr squared. So r is the radius of the disk, because here what's rotating is the entire disk. So remember I said r is from the axis of rotation to where the mass is. So for this one, it's from the center of the disk where it's rotating around to the edge. And so we get that for a disk is 1/2 mr squared. Let's see, alpha, how can we get that? Let's see, we have d omega dt is alpha. Okay, so for this one, I have a final and I have an initial and a final, I have a time, so I can jump right to alpha. For the net torque needed then, all I need is the inertia. Well, I'm given the mass of it. This is the mass of the merry-go-round because I didn't want to write it out twice. So the mass of it is this 3.1 times 10 to the 4th kilograms. And I've been given the radius. So I have everything I need to calculate the I. So we can write this out if we want as then my torque net. Torque net is going to be, let's see, for my I, 1/2 mr squared times my alpha, d omega dt. So let's put in our values. 1/2 times the mass of the merry-go-round, 3.1 times 10 to the 4th, 10 to the 4th kilograms, times the radius, 7 meters squared, times omega final is 3 radians per second, so 3 radians per second minus 0 radians per second. And the radians is the key that I am in omega, because this is already in radians. If it were rotations, I would have to make that conversion with the 2 pi. And then t is 24. I put all that in, and what do I get? I get that the net torque is 9.5 times 10 to the 4th Newton meters. Pretty big, but I would expect that. I mean, that's a pretty large mass to get going. So this would be like the amount of torque that the engine would need to put out for actually rotating it, for whatever mechanism they have below. There you have it. So that's our first make something go, and incorporating our equations of motion into this new force, just like we were doing with going up a hill.